Let's put everything we've discussed together in the previous lessons together to make a set of gas law equations. First, we need to remind ourselves of what we've seen already. According to Boyle's law, volume is inversely proportional to pressure as long as temperature and amount of gas are kept constant. And because of that, the volume of a certain gas multiplied by its pressure equals a constant. This can be used to solve questions by proportion. We saw that P1 V1 equals P2 V2. Then we saw that pressure is directly proportional to temperature. That's only true if the other variables, volume and amount of gas, are kept controlled. Because of this, pressure divided by temperature always gives a constant value, and so we can derive the formula P1 over T1 equals P2 over T2. Then we saw from Charles's law that volume is directly proportional to temperature as long as we control for the other variables, pressure and amount. Because of this, volume divided by temperature gives a constant value, and so we can derive the formula V1 over T1 equals V2 over T2. So for our first general gas equation, we can simply put all these three equations together, these three proportion equations. You see, what happens if you have two states and all three of these variables, temperature, volume and pressure, are varied between the two states? In other words, only the amount of gas is constant. So we have a trapped gas, so gas can't come in or go out. So the amount of gas inside our container is constant. But we have this gas under two conditions, and between the two conditions we vary temperature, volume and pressure. How will we be able to solve for an unknown value in this kind of case? We simply put these three proportion equations together and we get P1 V1 over T1 equals P2 V2 over T2. Let's get a question to actually see how we can use this. A gas bubble at the bottom of a lake has a volume of 200 centimeters cubed at a temperature of 8 degrees Celsius. Then this bubble rises, and when it reaches the surface, the temperature is 15 degrees Celsius and the pressure is 100 kilopascals. Its volume increases to 550 centimeters cubed. You need to calculate the pressure on the bubble when it was at the bottom of the lake. So notice that we have a question state, that's the bottom of the lake, and a comparison state, the top of the lake. Now often we call the question state the second state and the comparison state the first state. But in this case, first the bubble was at the bottom of the lake, then it came to the surface, so somehow it feels right to say that the first state, which is actually the question state, is down at the bottom of the lake, and the second state is at the surface, but it really doesn't matter. So I'm going to call that V1, that T1. We have to find out P1. Here we have T2, P2 and V2. However, we can't use the temperatures in degrees Celsius. So the very first step is we convert this into Kelvin. Add 273 to each of these, and there we find the converted values. We substitute values into the equation, solve for P1 and find our answer. The unit is kilopascals. How do we know that? Because P2's unit was in kilopascals. When we use this equation, P1 and P2 must have the same unit as one another, V1 and V2 the same unit as one another, and temperature must be in Kelvin. But now, what if we have two states of gas, and between the two states all four of these variables change? Temperature, volume, pressure and amount. Not one of them is controlled. In other words, how do we put the factor of amount of gas into our equation? In order to do so, we need to reason through the relationship between amount of gas and pressure and then know where it fits into the equation. So let's do just that. Amount of gas is measured in moles and its symbol is N. So let's think a bit. If we were to pump more gas into the simulation while we keep the other variables constant, we keep our finger on the lid so that the volume can't change. We make sure that the temperature remains constant. The only variable that we change is that we add some more particles. Well, let's see what happens. Let's run the simulation. Notice that as I pump more particles into this container, the pressure rises. There are more particles inside to do more hitting against the sides of the container, and so the pressure rises. As the amount of gas increases, the pressure increases, and this is, in fact, direct direct proportion. So pressure of a gas is directly proportional to the amount of gas. Now we saw that temperature is also directly proportional to pressure. So wherever temperature appears, amount of gas must appear alongside it in the equation. And so it must be at the bottom of the equation together with temperature. P1 V1 over N1 T1 equals P2 V2 over N2 T2. Let's use this equation to answer a question. 1 mole of gas at 101,3 kilopascals and 273 Kelvin has a volume of 22,4 decimeters cubed. What is the volume of 5 moles of gas at 120 kilopascals and 280 Kelvin? So notice we have a question state and a comparison state. And between the two, all 4 of those variables are changed. Pressure is changed, temperature is changed, volume is changed, and amount of gas is changed. Let's call the question state state 2 and the comparison state state 1. So that's N1, P1, T1, V1. N2, P2, and T2. The temperature is already in Kelvin, so we don't need to convert that. We can simply substitute into the equation and solve for the unknown value V2. We find the answer, and its unit, decimeters cubed, is the same as V1's unit. Now, did you notice something interesting about the comparison state I used? 273 Kelvin and 101,3 kilopascals. Are those values familiar to you? They are called standard temperature and pressure, STP. 273 Kelvin is actually 0 degrees Celsius, and 101,3 kilopascals is atmospheric pressure at 0 degrees Celsius at sea level. And so those two values were chosen by scientists for whatever reason. It was just they had to pick something, so they chose those. They were chosen to be called standard temperature and standard pressure, STP. Now, can you remember learning that a volume of 1 mole of any gas at STP is 22,4 decimeters cubed? So this is true always. So I was actually using a comparison state that is known and is often used as a standard to compare other things against. I could have used any comparison state. Any other comparison state would have been proportional to this comparison state. So for any set of values that's actual data, not just data that's sucked out your thumb, the answer to the pressure times the volume divided by the number of moles times the temperature would be the same as what we got here. What is that answer? Let's do the calculation and we find 8,3. 8,3 is a very special number because any pressure multiplied by its volume divided by the number of moles of that gas that's trapped and its temperature in Kelvin will give 8,3 if the units are right. We'll speak about that later. And so, since this constant is not just a variable constant as long as you control for whatever other variables, we don't just use a K for it. We give it a special name and a special symbol, and the symbol the scientists decided on is R. R is 8,3. We'll get to what its units are just now. So 8,3 equals P2 V2 over N2 T2. But the way we've written this now, we don't have a question and a comparison state. Well, we do, but we already know the number for one of them. It's 8,3. And so we don't need these little 2's anymore. We can simply write 8,3 equals PV over NT. And then, since 8,3 has been given the special symbol R, we can write R instead of 8,3. Let's clear the fraction to make the equation look nicer. We multiply both sides by NT and then we rearrange. PV equals nRT. And this is the form in which we write the general gas equation usually. PV equals nRT. So we can use this equation to solve for a situation where we don't have a comparison state, we only have a question state. In fact, it is still using a comparison state, but it's just that the comparison state is known. We don't have to be told it in the question. Or maybe we could say the comparison state is universal. It applies in all situations. And that's why we don't need to be told it in the question.